Hello student, myself Nimesh Prabhakar. Welcome to Antenna and Propagation lecture series. In my previous lecture, we discussed about the introduction of antenna array. Then we discussed about the different types of the array like broadside array and fire array. Then other two types of the array and basic condition for the point source analysis. So now we start lecture. So in this lecture we discuss about the 2-point source with current of equal magnitude with the same phase. So here we consider 2-point source, and that point source we give the equal magnitude current and equal phase current. So now we start the analysis. So here this is the figure for this. This A1 and A2 is this 2-point source we consider here. So consider that 2-point source A1 and A2 separate by distance D as shown in the figure. So we have placed these two source A1 and A2 and the distance between these two is the D. Consider that both the point source are supplied with the current equal in magnitude and phase. So this is the condition for us. Is the current we have given is the equal magnitude and the phase is also equal. Consider the point P far away from the array. So here in this figure we can see this is the point P. This is the very far from this antenna array. Let distance between the point P and the point source A1 and A2 be R1 and R2 respectively. So the distance between this point P and this A1, that means this is the A2 and this is the A1. So distance between the point P and the A1 is the R1, and distance between the A2 and the point P is the R2 respectively. As these radial distances are extremely large as compared with the distance of the separation between 2-point source D. So here we have assumed that this distance between the point source P and this P point is very large as compared to distance between these 2-point source D. So we can write as R1 is equals to R2 is equals to R. That means both the distance are the same we have considered. The radiation from the point source A2 will reach earlier at the point P than the from point source A1 because of the path difference. So here from the figure we can see the radiation from this A2 is reached the earlier at the point P as compared to this radiation R1. It requires the large distance. It requires more distance to reach this point. So because of the path difference. Hence the path difference is given by, so we can write the path difference is equals to d cos phi from this figure. The path difference can be expressed in terms of the wavelength as, we can also write the path difference in the terms of the wavelength as d cos phi by lambda. So the phase angle we can write from this equation as phase angle is equals to 2 pi into path difference. So we have the equation for the path difference. So when we put this, so we get the psi is equals to, that means phase angle is equals to 2 pi d cos phi upon lambda. So we get the 2 pi by lambda into d cos phi. But the phase shift beta is equals to 2 pi by lambda. So the value of the beta is equals to 2 pi by lambda. So we can write this equation as, so instead of the 2 pi by lambda we can say that's beta d cos phi. So we get finally the phase angle psi is equals to beta d cos phi, and the unit for this is the radian. Now here we consider as E1 is the far field at a point P due to the point source A1, and we consider this field E1 is equals to E0 e raised to minus j psi by 2. Same as E2 is the far field at a distance point P due to the point source A2. And the value for the E2 is equals to E0 e raised to minus j psi by 2. So the total field at the point P we can write as Et is equals to E1 plus E2, because here we get these 2 point source field at here, E1 and E2. So we can write Et is equals to E1 plus E2. So from the both the E1 and E2 we take the E0 is the common. So we can write Et is equals to E0 e raised to minus j psi by 2 plus e raised to j psi by 2. So from the here we multiply and divide both the side by the 2. So we can write this equation as 2E0 e raised to j psi by 2 plus e raised to j psi by 2 e raised to minus j psi by 2 by 2. By trigonometric identity, we have equation like this: e raised to j theta plus e raised to minus j theta by 2 is equals to cos theta. So now from this identity, we can write this equation number 1 as Et is equals to 2E0 cos psi by 2. So instead of theta, here the psi by 2. So we get the total field as Et is equals to 2E0 cos psi by 2. So, and we have the value, the side, the phase angle is the beta d cos phi. So we put here 2E0 cos beta d cos phi by 2. Now the array factor. So what is array factor? The array factor is the ratio of magnitude of resultant field to the magnitude of the maximum field. So the equation for this array factor is AF is equals to magnitude of the resultant field ET and the magnitude of the maximum field. This is the E maximum. But the E maximum value is the 0, because we know that the maximum is when the theta is equals to pi by 2. Sorry. So we get the E maximum is equals to 2E0. So when we put here in this equation like the AF is equals to ET upon 2E0, and we have the value of the ET is equals to E0 in the cos theta beta d cos phi. So when we solve this, so we get the cos beta d cos phi by 2. This is the array factor. So array factor become cos phi d when we put the value of the beta is equals to 2 pi by lambda. So we get the pi d cos phi by lambda. So now we find the maximum direction for the 2 point source with current equal magnitude and with same phase. So the total field is maximum when cos beta d cos phi by 2 is maximum. This is the condition for the maximum direction. So the maximum condition for the field is given by cos beta d cos phi by 2 is equals to plus or minus 1. We can write. So now consider the spacing between the point source is the lambda by 2. So d is the spacing between the source. So instead of that, we write here the lambda by 2. So cos beta lambda by 2 cos phi by 2 is equals to plus or minus 1. So, and we put the beta is equals to 2 pi by lambda. So cos pi by 2 cos phi is equals to plus or minus 1. So now we solve this equation like this. Cos term goes in the right hand side, so it becomes the cos inverse plus or minus 1, and cos inverse plus or minus 1 is nothing but plus or minus n pi we can write. So where the n is equals to 0, 1, 2, 3 up to n. If now we take the n is equals to 0 in this equation, so we get pi by 2 cos phi maximum is equals to 0. We have put here the n equals to 0. So when we solve this, like the pi by 2 is also become the 0, and the cos inverse 0, the phi becomes the 90 degree or the 270 degree, because the cos value is the 0 when the 90 degree and the 270 degree. So for the maximum radiation for the 2 point source is in the direction of the 90 degree and 270 degree. Now we find the minimum or the minimum direction. So the total field is minima when cos beta d cos pi by 2 is minima. Hence, the condition for minimum field is given by cos beta d cos pi by 2 is equals to 0. So now we consider same, the spacing between these two elements is the lambda by 2. So we get the cos beta lambda by 2 cos pi by 2 is equals to 0. And we also put the beta is equals to 2 pi by lambda. So finally we get the equation cos pi by 2 cos pi minimum is equals to 0. So when we solve, the pi by 2 cos pi minimum is equals to cos inverse 0. And the value of the cos inverse, that means the cos inverse 0 is nothing but we know that the 2n plus 1 pi by 2. So if we take the condition same, n is equals to 0 here. So when we put the n equals to 0, we get the pi by 2 cos pi minimum is equals to plus or minus pi by 2. So pi by 2 cut. So we get the cos pi inverse is equals to 1. So the pi minimum is equal to cos inverse 1. So when the cos inverse is 1, when the pi is equals to 0 or the 180 degree. So this is the minimum direction for this. Same, the half power directivity. So the condition for the half power point is given by cos beta d cos pi is equals to plus or minus 1 upon under root 2. This is the condition for the half power direction. Now we know that we take same assumption like the beta is equals to 2 pi by lambda and the distance between this is the lambda by 2. So now we put this condition in this equation. So we get the cos pi by 2 cos pi is equals to plus or minus 1 upon under root 2. So pi by 2 cos pi is equals to cos inverse plus or minus 1 upon under root 2. And cos inverse plus or minus under root 1 upon 2 is nothing but plus or minus 2n plus 1 pi by 4. Now we take the n equals to 0. So we can write the pi by 2 cos pi half power bandwidth is equals to plus or minus pi by 4. So when we solve, we get the half power point for this is equals to 60 degree or the 120 degree. So this is the half power point for the 2-point source with current equal magnitude and with same phase. And fill pattern. So here we see the fill pattern for this 2-point source. So the maximum radiation we know that for the is the phi is equals to 90 degree and 270 degree. Same as the minimum radiation when the phi is equals to 0 and phi is equals to 180 degree. And this half power point when the phi is equals to 60 degree or 120 degree. So this is the field pattern for the 2-point source with current of equal magnitude and with same phase. So in this lecture we discuss or analyze 2-point source with current of equal magnitude and with same phase. Thank you.